Hello everybody. Welcome back to day 2 of Pawsey Bootcamp. Before I get started today on our lecture on quantum Fourier transform, I want to do a brief recap and a summary of what we learned yesterday. But I also want you all to ask any questions you have right now before we move on to a new quantum algorithm. In my recap, I'll go through Dirac notation, Deutsch's algorithm, and then the development on that, the Deutsch algorithm, which generalizes to n-qubit case. Okay, so I'll start with Dirac notation. So first of all, do we have the link to share the recap link for Dirac notation, the cheat sheet? The cheat sheet we have? Yeah. Okay. So that will be shared with you. But okay, so let's go through the very basic stuff. So for example, let's go through the ket notation, right? So ket notation, so basically, which is represented by this thing. We learned that a zero vector, which is 1, 0, is written like this, and then the one vector, I'm using the notation represented by, okay, and then the one vector, which is 0, 1. So this is basically your ket notation, and then the bra form of that is just this guy is represented by this guy, and it's just it's conjugate transpose of. So bra is defined as a conjugate transpose. Let me not use the parenthesis. Something like this. And this just means transpose it and take complex conjugate. So it's just be 1, 0. Okay. And same with 1 as well. Okay. Pretty simple stuff here. The other thing is when you compute measurement probabilities, so measurement probability, let's say you are computing the computational basis, which is the G operator. I told you that yesterday in my lecture, before my lecture on Deutsches Georgia, that it can be written like this. Know that the matrix form of this is just 1, 0, 0, minus 1. You can simply read off the eigenvalues as 1 and -1. This is also known as the phase flip operator because it takes the state 0 and it outputs 0. But it takes 1 and then it outputs -1, right? So yes, so the probability of measuring the state 0 here. So if you want to measure probability, if you want to measure the state 0, the probability we said, okay, so let me just write it a general form. It's simply written like this. So so it depends on your final state, right? So let's say you're trying to measure one of the eigenstates, 0 or 1, which is I, given that your final state is, let's say, psi. Okay, so let me just write it down in words to not confuse anyone. Given the state is psi, the way you would do it is you just take the inner product with this and then norm squared it. Okay, so as an example, let's say your psi is the plus state, which is the 1 over square root 2, 0 plus 1 state, and I is 0, then you can see that probability of getting 0 is just the norm squared of 0 with the plus state, right? And you can simply read off that inner product of 0 with 0 is just 1, and then 0 with 1 is 0, right? So that's another thing. I should also write it down. So it's just going to be 1/2 because of these things I mentioned. So 0, 0, if you take the inner product, it's 1, and then 0 with 1 is just 0 because these are orthogonal And you can also verify this by using the column row vector multiplication. Okay, so this is the only math that we need to get to, and this is sort of the basic direct notation that you need to know. Any questions on this? I hope we're all on the same page, because this is the basic grammar that we need to have in our tool set before we learn about algorithms. Any questions? Okay, so the second one, which is the Deutsch's algorithm. So we learned that this guy called David Deutsch, who proposed a quantum circuit to essentially check if a function that acts on binary string xy and gives out some other binary string. So let's say x1. Well, let me just write it down like this, where both x is a binary string. So this just means, okay, is in, this is just a set. So x is allowed to have two values and y is also allowed to have two values. So Deutsch's algorithm only applies to this single bit case. So, and in classical case, we said that to check if a function is constant or balanced. So constant means fx equals to fy, and then balance means fx is not equal to fy for all x and y. So, this is the case for one bit case, by the way. So you can just say this is not the case, or you could also say fx equals to fy for half of the case, to be more precise, for half of the cases. So there was a little bit of confusion that I caused yesterday, because I said that in the classical case, you need to query it at least twice. But that's not true, actually. You just need to query it twice. The reason for that is because you only have two possible values, right? F0, F1. And if you compute these two values, then you'll know whether the function is constant or balanced, because x can only take two values, right? 0, 1, and that's it. That's all you need to check. But in the quantum case, we needed a single query, right? So this was two queries for the classical case, and in the quantum case, it was a single query. Okay, this is what we learned. The reason for this, why quantum computing shined, is because of the ability to have this principle of superposition, because we started with this initial state 0, 0, right? And then we were allowed to create this superposition state, the plus state, and then to be able to act this unitary UF on both gates, and then apply Hadamard gate here, and then just measure on the computational basis. Sorry, I suppose this should be the one state. Okay. So why was quantum computing able to solve this problem with a single query? The reason is basically because of principle of superposition. That's one. Okay, so I'll write it down as parallelism. And the second reason for that is to be able to implement UF, which is a 2-qubit gate in this case. And this was generalized to this second algorithm, the DZ algorithm, Deutsch's algorithm. So this was generalized to the n-bit case. So instead of having just two values, 0 and 1s, now you can have 0, 1 to the n. This means that I can have values like 0, 0, 0, 0, 0, 0, and then 0, 0, 0, 0, 1, so on and so forth. So you'll have 2 to the n different if you want to check if your function is constant or balanced. Constant means it's going to give you 0 all the time, and balance means it's going to give you 0 half the time and 1 half the time. In the classical case, in the worst possible scenario, what do you need to do? You need to do 2 to the n divided by 2 plus 1 queries. The reason for that is, let's say you have 100 different strings, right? Then you need to, in the worst case, you need to measure it at least 50 times and then plus 1 times to do the tiebreaker. If you got lucky, obviously you won't have to do 50 times. On the second or third time, you might be able to figure out. So you basically need to continue doing this until you get a 1, right? So let's say you take a random bit string, let's say, I don't know, 1, 0. You get 0, right? And then try another one. Let's say you get 0. Keep on doing this until you get 1. And if you got 1, then you know that the function is balanced, right? But in the worst case, you might not get 1 until the 58th case. And so you need to run an extra one to do the tiebreaker. Okay, so anyway, so these constant factors actually don't matter. So this is just big O of 2 to the n if you want to talk about the complexity, which means it takes exponential in n queries to figure out whether the function is constant or balanced. But in the quantum case, I didn't prove this myself. It only takes 1, right? And that was the big punchline that this algorithm has. And this uses the same principle as the first case, but it just generalizes it to n qubit cases. Okay, and this is where we saw the strength of quantum algorithm. Now, I told you that this problem is not practical, right? In real life, we don't really care if the function is constant or balanced or not, right? If we want to solve practical problems using quantum computing, might as well focus on something that has a real value. And this is where Fourier transform comes in, and the quantum version of that comes in, which I will get into in this page. But before this, do you have any questions about this Deutsches and Deutsches-Sosa algorithm? Recap of U to both qubits. So you mean like do this example for 2 qubit case, is it? Is that what you mean? So this is right now, this is a single qubit case. We're using 2 qubits right now, but this is just the ancillary qubit. Let's just explain how unitary F is applied to both qubits. Okay. So unitary F, right? It acts on X tensor Y to give you X tensor Y XOR Fx. Okay. So all right, so let's do an example. So let's say X is 0, the bit string X is 0, and Y is 0. Then UF acting on 0 tensor 0 is just going to be 0 tensor. So Y is what? 0, right? 0 XOR F of 0 is an example. So I told you that this XOR, when you have 2 inputs on the XOR, on the left and the right, this gives you 0 if these are the same, and it gives you 1 if these are different, which means if F of 0 is 0, the outcome of this will just be 0, and F of 0 is 1, the outcome will be 1, right? Which means I can just simplify this as F of 0. The property that I use here is, as I said, 0 XORed with any bit string Z, it's just Z, okay? And so this is an example of how you would use this gate UF. Does that answer your question? Okay, great. All right, so we're out of time for the recap, way out of time. So let's just jump into QFT. I have lecture slides first, so I'll jump into that, and then we'll have the hands-on session. So it's very important that you understand the math of QFT. The reason for that is Jonas is going to give you a lecture on QPE, the quantum phase estimation algorithm. So QFT is a subroutine to multiple algorithms that are different, that are important in quantum computing. Because it is a subroutine, we will focus on the absolute mathematical detail of this algorithm. Okay. And then we will sort of like give you a high level idea of like algorithms that will follow later. So please pay attention to QFT and how we can build a quantum version of Fourier transform. So let me just make sure. Okay, you can see my slides. All right. So before we get into QFT, can someone tell me anything about classical Fourier transform? Why do we use Fourier transform in the classical context? I'll be looking at my chat. Transform a function from real to reciprocal space, right? So that's that's correct. So that's the mathematical map, right? So you have a function in the real space, you transform it to momentum space or the reciprocal space. But why do we need this? Why do we need the Fourier transform? Can you give me an example of where it is useful? Spectral analysis. Thank you, Christopher. So Fourier transform is useful when you have to understand spectral content exactly. So let's say you had a data. For example, let's say you have a signal. You're recording the audio of my voice, and you process the signal, right? And then you essentially have this time series data. If my voice had any noise, to essentially wipe out the noise, what you can do is you can transform it from this space to momentum space, and then there you are able to filter out the noise. This is one example of where Fourier transform is useful. If you haven't heard of Fourier transform before, I would highly recommend you to check out it online. But because this is a lecture on quantum version of Fourier transform, I'll just jump directly into what it's all about. So QFT, as I said, it's a quantum algorithm for applying the discrete Fourier transform to the amplitudes of a quantum state. So Fourier transform, right? There are two versions of it. One is the continuous Fourier transform, which means it acts on a continuous function. But because the real life in real life, for example, if you want to record my voice, the recording of the voice will be in discrete samples. So we need to discretize any continuous function, and that's the idea of discrete Fourier transform. So essentially, think about a line. Line has infinite points. Discretizing it is dividing it into chunks, right? So let's say 0.1, 0.2, like that, right? So that's the idea of discretizing it. And then once you discretize it, then you do the Fourier transform on the discrete numbers instead of doing it on a continuous function. Okay. So the mathematical description of this would be, so the classical discrete Fourier transform looks something like this. Okay, so you have some function, some vector f0, some function small f, that has essentially n amplitudes. So f0 all the way to fn minus 1. And these are complex numbers. So basically what discrete Fourier transform does is it converts this from the real space, which is the vector f, to the momentum space or the reciprocal space. And that does that by basically exponentiating this these values where so for example, so y actually goes from all of the indices of your vector. And so you take for example, you take f0 and you exponentiate it with this 2 pi over n times xy. X is basically the index of your vector, and y is also the index of your vector as such. So I'll write this on my iPad so that it's so that I can explain it step by step. Right now I'm just reading an equation. But all you need to know is that this is a procedure that is very useful in real life. As computer scientists, as algorithm designers, what we care about is how many operations do I need to do in order to compute this, right? And so if you look at this, you can actually do this by n matrix with order of n square operations. The reason for this is, okay, so I'll get into this on my iPad because it's hard to read. And then I'll talk about how a quantum version of that works. And then I'll talk about how the quantum circuit for implementing QFT works. And then I'll get into the complexity analysis. Okay, so that will be the way that this lecture will go. So because I don't want to switch back and forth, I'll just go directly into my iPad. Okay, great. So as I was saying, I will have to speed up a little bit. So classical Fourier transform, it works, it's a map, okay? So it is basically a map that works something like this. So you have a vector, let me use a different color. You have a vector fx. So f is a complex function. Okay, so this is going to be f0, f1, all the way to fn. And then your capital F is going to be another complex function that is going to look like this, f0, fn, okay? And so fx is actually related to this guy, fy, by this, that's what I said, where x is 0, 1, and -1, okay? So to do this operation, right, if you focus on this equation, to do this operation, look at individual points, right? So for example, if I want to compute f0, just the first index, what do I need to do? I need to go from every single y, fy, x is 0, 0 times y, right? So this is just 1. Okay, so I'll just write it down like this. So if you focus on this, you'll find out that you'll need order of n square operations. The reason for this is because if you write down the matrix, you can essentially represent this as a matrix vector multiplication. Okay, so you'll need n times n plus n operations. So this n corresponds to the number of rows of your matrix. Okay, this n corresponds to the number of multiplication you need to do. And this n corresponds to the number of additions you need to do. That is the complexity of matrix vector multiplication. So I invite you to do this on your free time and verify that this is indeed the case, because I will have to speed up a little bit. So this is the classical case. Okay, so we haven't moved to the quantum case yet. So but all you need to know is it takes n square operations to do discrete Fourier transform. Okay. Now, the fast Fourier transform version of this is an improvement on it. Now, people who are specialists in spectral analysis, they're probably familiar with it. If you don't know, that's okay. So what a fast Fourier transform does is it essentially reduces the the complexity from n squared to n log n. So basically what this is doing is this n squared is basically n times n. So it's reducing the second n into log n. Okay. If you want to look at it again, check it out online yourself. But what we're interested in for the purpose of the lecture is QFT, right? And the question is, how many operations does it take, right? Can we do better than this? And this is where QFT comes in. So I'll write down the QFT map. So QFT, or like going from classical to quantum, is just moving from bit strings to states, right? Just like how bit 0 is written at cat 0, you can probably guess. You can make a guess, right? So if you just look at this map, make a guess and tell me, what does the quantum version of this look like? So this is written like something like this. So let's say you had a number x, right? What you do is you actually go from x to 1 over square root of n, y equals 0 to n minus 1, e to the I 2 pi over n, x, y, y. So the quantum version of this is the state x transforms to state y with this same amplitude as classical case, okay? So the only thing is here we had a number, fx. Here I'm calling this as a state x, okay? And here we had a number fy, and here I have a state y. Okay, so this is the map that we start from. This is the quantum map that I want to implement, okay? And I obviously, if you want to do any algorithm, I need a quantum circuit. So I need to devise a quantum circuit, and I need to look at the complexity of it. Okay, so this is the simple process of going from classical to quantum. Any questions on this? Any questions on the DFT or FFT? Okay, so I will assume that so far you're following along. It will
Dikshant,
start.
there
Yes.
is a question in the chat.
Yes. Is the exponent related to the phase? Yes. So the exponent is indeed, you mean this exponent, right? And by phase you mean, the phase that appears with a state. So for example, like phase like this, phase that appears with a state 0, I suppose. So this is indeed a phase, but notice that this is not just any phase, because this appears in a sum, right? So what I basically have is, okay, so let's focus on what this tells me is, let's say I focus on just a 2-qubit case, right? So what I'll have is I'll have 0, 0 with e to the I 2 pi over n. I'll talk about how to implement this, by the way. Okay, so stay patient, because right now this is just an integer form. We need to go to the binary form, because why? Because this is a binary number, right? Because all of these are binary numbers. 0, 0 is a binary number. How do you multiply 0, 0 with 0, 1, right? I haven't gone into that. So I haven't defined how to multiply this, but stay tuned on that. So it will look something like this. I'll tell you how to do this, but yeah, so indeed there will be phases like this, right? So 0, 1, e to the I 2 pi over n 1, 0, and then the last one, e to the I 2 pi over n 1, 1. I haven't told you how to multiply this, so don't worry. So you actually don't do 0 times 0, 0, 0 times 1, 1, because that's not how binary multiplication works. Here, notice that this was just because this is a binary string. We have to be careful about how to do this. But this is how it works. And the reason why it is non-trivial here is because each of the phase before each of the state is unique. So we need to figure out how to implement this this phase as a quantum circuit. Okay. That's a very long answer to your question, but I hope it answers it. Okay. So delete. Okay, so let's walk into. So I'll do this step by step. Okay, so I haven't told you how many operations we need to do. We'll calculate it ourselves before I even tell you the answer. Okay, so step one of QFT is first is what you do. What you do is you write your x. So write x as an integer. 0, 1, n minus 1 in binary representation. What do I mean by that? Because notice that these are bit strings, right? So example is, let's say 0, 0, 0, 1 for the 4-qubit case. And example is, let's say 1, 0, 0, 0. Okay. Suppose, let's say we start with just the initial state, this. Because it is a bit string, we need to transform it to an integer. And so this bit string, this general X, will have how many strings? It will have n strings. Something like this, right? Okay, so let me remove the cat first because we only want to focus on the bit itself. So this can be transformed into integer form. So I hope all of you know this, that n-bit integer, n-bit string can be transformed into an integer like this. So what I'm doing is I'm transforming from integer, for example, 5 is 101, right? The reason for this is 5 is what? 1 times 2 to the 2 plus 0 times 2 to the 1 plus 1 times 2 to the 0. Okay. And so the phase factor in QFT, so this is the first step. And then the phase factor in QFT is defined as something like this. So your xy over n. So this will actually be your multiplication in the following manner. So notice that n, right? If I have n qubits, then I'll have 2 to the n possible bit strings, right? So this capital N corresponds to number of qubits. And this n corresponds to, the small n corresponds to, 2 to the n corresponds to the number of possible states. Okay. Oh, sorry, I think I'm doing it the wrong way. So this small n is the number of qubits. And capital N is the number of all the possible states. So if you, in discrete Fourier transform, right, you don't always have 2 to the n bit strings, right? You might have a number that is different from it, but you can always tile zeros to make it of size 2 to the n, right? So this indeed does work for a general case, not just for a case where it's 2 to the n. All right, so this is defined as, let me go back to the other color. So this is defined as 1 over 2 to the n, xn minus 1, 2 to the n minus 1, x1, 2, 1, x0, 2, 0. Okay, so I'll just show you how to multiply this. So all I'm doing is I'm writing down my x and my y in this binary form. Okay, y1 to 1 plus y0 to the 0. Okay, so the thing that I find most confusing is the step that follows here. And a lot of the textbooks, tutorials that do this, do it in a very confusing manner. So this is the only step that I would invite you to focus on and pay attention to. So when you multiply these two things, it's just a simple multiplication, right? So let's do the multiplication in the following manner. So let's multiply this with this. What do I get? I get yn minus 1, x0 divided by 2, right? Notice that I'm also multiplying it with 2 to the n. and 2 to the n times 2 to the n minus 1 is just 1 over 2, okay? Plus yn minus 2. So I'll do the same thing with the second term that I've written down here, and I'll multiply that with x1, so the first two terms, x0 over 2 squared. So first, I am slightly skipping a step here, but notice that if you multiply it, you'll get to this answer. The key thing to remember here is that I am essentially ignoring all the terms with power of 2 to the n or more, okay? The reason for that is because any number that comes as 2 to the n, over 2 to the n, for example, 2 to the n plus 1, this is going to be a very small number as n is large. So the precision that I'm aiming for is 2 to the n. So I will be ignoring all the terms with power larger than this. And with this assumption, we can simplify this expression into this, okay? So I would highly recommend you to pay attention to this and maybe look back at the recording and make sure that you understand how this follows. And this is being ignored. As an example, if you multiply this with this, you'll get 2 to the 2n minus 2, right? Which is much larger than 2 to the n. And we're ignoring terms like those, okay? And the second confusing step is defining binary fractions. So far all we did was we just wrote down the definition and then we expanded this phase factor, okay? So we haven't done anything yet. So define the binary fraction, this terminology. So dot BL plus 1 all the way to B little l plus capital L. And so this is defined as, notice that as an example of this would be something like 0. So basically decimalizing binary numbers, but after in this manner, okay? So it would be something like this. So I'm starting, my first bit string is BL, my last one is BL plus capital L, which is the total length of this bit string. And so it would look like something like this. 2 to the 2, 2 to the L. So we're supposed to end this first lecture at 9:45. And so the hands-on will be slightly shorter because this is going to take longer than I expected, also because of the first recap. All right, so I'll keep on continuing. So once you define this binary fraction, okay, so this is your step 2 of your QFT. Okay. I hope you're making small notes. You don't need to copy like every single step because you can always look back at it. But try and make like small notes. Make sure that you're following, at least make a high level note where you're writing down step 1 or step 2 or something like that, so that you'll remember it. Okay, so yeah, so once I define this binary fraction, then what I can do is I can continue rewriting this. So I can simply write this. After I define this binary fraction, it's very simple to write x0 over 2. So can someone tell me what x0 over 2 is in binary fraction? If this is defined like this, what is x0 over 2? So I have this form here. I will need to write it down as this form. So I have this x0 over 2. What is it? Okay, so I see, okay, that was a previous message. Any guesses? One. Do you mean 0.1? See, half. Remember that I still have x0. I don't know the value of x0, right? So I would need, so as an example, if BL point BL plus 1 all the way to L plus 1 is defined like this, then what would be x0 over 2, which is on the right side. So I basically have x0 divided by 2 to the 1, right, on the right side. So what would be my left side on the as a binary fraction? So this is just using the definition, right? So any guesses? So Sharif, you have the half, but you also need to multiply that with x0. Okay, so it would just be something like this. So it will be just dot x0.
I think it might be more. It might make a bit more sense if you put the 0 point something.
Oh, right.
If you put the 0 in front of the dot.
Okay, so let's do that. Maybe this might be causing confusion, right? Okay. So this will just be 0 point x0, okay? So this is the definition of binary fraction. And so I'm just using the definition here. And I'll do the same with the second term. Okay, so can you tell me what the second term will be? So I want to write down this term, this guy, using this definition. So what will it be? 0 point something? So 0 point x0 plus 0 0.0 x1. Thank you, Nima. So it will be 0 point, because I'm basically using the definition, it will just be 0 point x1 x0. The confusion might be, remember that as I keep on increasing the length of the strings, I'll have more and more terms, right? So BL is corresponding to this first term, BL plus 1 is corresponding to the second term, and then BL plus capital L is corresponding to the last term, right? So if I only have a single term, then I'll have x0. If I have two terms like this, where you have 2 and then 2 to the 2 like this, then it will just be x1, x0, okay? So can you tell me the last term? What will be the last term? 0 point. So I need to rewrite this. Yes, so x0, x0 all the way to xn. Now which one is it? Is it x0 all the way to xn, or is it xn all the way to x0? Notice the ordering. If I have 1 over 2 here, it starts with it starts in the beginning, right? So if I have 1 over 2, this should be the first string, correct? So it will be x n minus 1, n minus 2, all the way to x0. Okay? So this is basically what we did here was we wrote down our map, we simplified it into this term. Okay, so that's all we do. That's all we did so far. Now what we can do is we can evaluate this. QFTX, right? Because now we have written down the definition of this this phase factor into this form. We can evaluate this, and you'll see why we actually wrote this down. The entire purpose of doing this. Okay, so this will be my step 3 after I define my binary fraction. So step 3. Okay, step 3 is what I do. I do the following. So QFTX, I write down this as 1 over square root of 10 n. So I'll write down the definition again. 2 pi x y over n. So you saw how xy is multiplied right here. Now what I do is I just copy paste what I wrote down. So I'll use the definition I defined for capital N, right? Remember, capital N is just 2 to the n. Okay, and if I have square root of that, then I'll just have square root of 2 to the power of n. Okay, sorry, small n. And so y equals 0 to 2 to the small n minus 1. And I will basically expand this out. Okay, so what I'll do is I'll just copy paste it. Okay. Now I will also expand this state y as this state, remember, was defined like this. So y is just yn minus 1, yn minus 2, all the way to y 0. Okay. Just using definition here, nothing. So y, remember, y is a binary number. So y is just yn minus 1, yn minus 2, y0. So just to make sure you're not confused, if this is a 4-qubit case, an example would be if you have an integer, let's say state 4. Okay, so if you have a state 0, 0, this would just be 0, 0, right? If you have 0, 1, then this will be 0, 1. But actually this in integer form would look something like 0, and this would become 1. Okay. Just to avoid any confusion, this will later be transformed into integer format. And don't be confused by it, because all we did was we converted the binary into integer. Okay. So all I'm trying to say is that it's a binary string right now. Okay. And I am essentially substituting that. So now what you do is you expand this out. Okay, so I'm going to distribute 1 over square root of 2, and I'm also going to distribute the sum y, because remember this y is actually basically the thing I wrote here, right? I don't need to write down again. So and it's going to have all these possible values. So I can just write it down like this: yn minus 1, sum over y minus n minus 1. What possible values does it have? Just 2 values, right? Don't be confused that this y here is an integer, but then this integer y has this expansion, this binary expansion. So I'm going to distribute this in the following manner. So I 2 pi yn minus 1. Sorry, I need another number, dot x0. Okay, so I'll write down as 0.x0 so that you don't get confused. Yn minus 1. Okay, so what I did here is I took this first term. Sorry, I took this first term, and this is, what is this thing? Remember, this is just a tensor product, right? Tensor yn minus 2, tensor y0. So I, among all the possible sums in y, I took the first one, and then I took the first sum like this. Okay, and I'll do the same thing with the second term. Sum over yn minus 2, exponential of I 2 pi yn minus 2, 0.x1 x0, yn minus 2, all the way to sum over, I also have 1 over square root of 2. So I'm distributing across all of the n terms because I have n terms here. And I'll have I 2 pi y0, x n minus 1, x0, y0. Okay. So in step 3, I just substituted what I had expanded. And now what I'll do is, and this is we already have our expansion for QFT, for doing QFT. Okay, so let's look at an example for n equals to 3. Okay, so we can look at this term by term. So for n equals to 3, so before I go into n equals to 3, so we're done with doing the QFT expansion in terms of binary fraction. But let's look at n equals to 1, actually. So what happens when I have QFT on x0 using this definition? So I'll only have a single term, right? Can you tell me what this looks like? So remember that instead of having n terms, n of these terms, I just have a single term. In other words, I just have a single yn, right? So I'll only have this first term. And then I can just ignore the rest. So what will this be? Can someone tell me? You just use the definition. Anyone? Okay, so I'll just tell you the answer. So it seems like you might be slightly confused by what is going on here. But okay, so let's look at an example, right? So it'll just be 1 over square root of 2. Yn minus 1 has two possible values, 0 and 1, right? So when yn minus 1 is 0, this whole thing will just be 1, right? So I'll just have 1 times 0 plus when yn minus 1 is 1, then this will just be exponential of I to pi 0 times x0, 1. Okay. So it will just be this, and this can be implemented by 0 plus, okay, so let's write down the definition of 0 dot x0. What is it? It's just x0 divided by 2, right? 1. Okay, so I have an answer for QFT on x0. Okay, so what happens when x0 equals to 0? So when x0 equals to 0, I have QFT on 0, which is equal to 1 square root of 0 plus e to the I pi. Sorry, this is just 0, so I just have 1, right? So I just have this. And then QFT on one state is 1 square root of 2. You can verify this, it will just be 1. 0 minus 1, okay? When x0 equals to 1. Okay, so this is the plus state, this is the minus state. So how do I do QFT with just 1 qubit? What gate do I need to do this? Yeah, exactly. Hadamard, right? So to do this for the 1 qubit case, I just need to start from this state x0, and then I apply the Hadamard gate, and then I have QFT on x0, right? So this is my output state. I just needed to do Hadamard. Okay, very good. Now let's look at the 3 qubit case. So for the 3 qubit case, what you do is you have x, x2, x1, x0. Okay, so this is my input state. I apply QFT on it. If I apply QFT, what happens is I just use this definition, right? So the first term looks like this, the second term looks like this. Oh, yes, question. What happens to the exponential power? Oh, so if you look at the exponential power, I just simplified it, right? So this guy is, what is it? It's e to the I pi x0, correct? So x0, when x0 is 0, this thing is 0. Sorry, it's 1. So that's why I had a 1 here. Okay, I didn't write it down. It's just 1. When x0 is 1, then e to the I pi. So I just use the identity e to the I pi times 0 is just 1. And e to the I pi 1 is just e to the I pi. And e to the I pi is -1, right? That's the Euler's identity. Okay, very good. All right, so in the single qubit case, it's very simple. Now let's look at the 3 qubit case, and if you understand this, then we can then you essentially understand how QFT in general works. So this is, I just use the definition, okay? By now you should have sort of an intuition of how to use the definition. Just look at this expression and then just apply it, okay? Yeah, so the first term will just look something like this. 1. remember that the reason why I have 0 plus 1 is yn minus 1 has two values. So when it is 0, this is just going to become 1. And when it is 1, then I will have the exponent. Okay. So just substitution and nothing else. Please feel free to rewatch the recording and make sure you understand this. x0, 1. Tensor 1 over square of 2, 0 plus e to the I 2 pi dot x2, x1, x0, 1. Okay, so this would be the 3-qubit case. And so now let's look at individual terms, right? Now this is just a product state. So let's look at the individual terms. So this is your state, let's say y2. This is your state y1, and this is your state y0. Okay, so how to get y2? So let's imagine a circuit, right? Where you have x2, imagine a circuit, right? Where you have the first first qubit is in state x2, x1, and then x0. Then we get y2, y1, y0. Why? Because remember that this state is not entangled. We could write it as a product state, a tensor product, right? So we can just separate it out like this in a simple manner, because the state of the one qubit is not dependent on the state of the other. Okay, because we could write it out as a product state. So we realized that to get e to the I 2 pi dot x0, as we did here, okay, so I'm missing 0 dot in the beginning. So let me just write that down. So to implement this thing, right, which we did here, we just needed to apply the Hadamard gate, right? So you just apply the Hadamard gate. And we're done with the first qubit. Now for the second part, to get y1, now I have a problem because now I have x1, x0, right? So the question is, how do I get this? Well, just write it down. So e to the I 2 pi 0 dot x1, x0 is just e to the I 2 pi x1 over 2, 1, 2 to the 1, x0 over 2 to the 2. Use the definition. Then separate the phases out. I pi x1, e to the I pi x0 over 2. After you separate the phases out, look at the possible values. So the first one will be 1 if x1 is 0, and then -1, which is the Euler's identity, right? If it's 1. And then similarly, let me use a different color. This will be 1 if x0 is 0, and then this will be e to the I pi over 2 if x0 is 1. Okay. Now we have a condition where we have different answers depending on what x0 and x1 is, right? So again, if you look at this, it takes you to state 1 if its input is 0, and it takes you to the state -1 if the input is 1. What gate do we need to do this? What gate do we need to get this phase? We already looked at this, but I'm asking this again. To get this phase, what gate applies this phase?
Phase change?
The X gate. So, okay, so we are you're sort of getting to the answer. So I see X, the Z gate. So Basha said the phase gate, right? Z gate, phase gate. Okay, so let's look at the state carefully. Okay, so actually this is just the Hadamard gate. I can see where the confusion is coming from, Hadamard or the edge gate. The reason is because you also need to look at the state here, right? X1, X0. So you have X1 tensor X0. like this, right? So what we're doing is, if my input state x1 is 0, then it is transforming to the plus state. Oh, sorry. Okay, wait a second. So okay, let me rewrite this because I'm messing. Okay, let me rewrite this down here. Okay, so I separated these two different phases. Maybe let's make a little diagram where I have the first state and the phase. So let me write this. Let me rewrite this down as e to the I x1 tensor e to the I pi x0 over 2 x0. Okay, so let's go back up now. Let's go back up now to focus on what we did for the 1 qubit case. So for the 1 qubit case, right, where you had x0 transforming these to two different values, because we also have this summation, don't forget, as a sum of 0 and the 1 state with different phases. So when you have the sum, right, then notice that so this picture is missing here, right? So because what I need to get to is I need to get to the 0 plus e to the I 2 pi, and this x1 over 2 to the 1 plus x0 over 2 to the 2, x1 x0 state, right? So this is the state that I want to get to. And so, oh, sorry, I've already written this down as 1. So it is true that if you're just looking at this phase, the answer is the phase gate, which is what Basha and Sharif told me. But if I'm looking at this whole state again, right? And if I was just ignoring this part, then I would just need the Hadamard gate, right? Because what I have is with this, I have 0 plus 1. I'm missing 1 square root 2 divided by square root 2, and 0 minus 1 divided by square root 2. Okay, so the full state is actually given by the Hadamard gate. Okay, and the second state, which is this guy, remember, which gave us this phase. So this is given by, so you need to look at this not just as the phase itself, but rather 0 plus this state, okay, where we're considering the phase. So if you want to look at the second state, this is given by the control phase gate, okay, which applies this phase phase e to the I pi over 2 if x0 is 1, right? Otherwise, it just remains 1. So you can see that this is going to be a 2-qubit gate, right? Because if it is 1, remember, just like C naught, if it's 0, it doesn't do anything, and then otherwise it applies some kind of phase, the control phase gate. Okay, and this is the second term. So I'll tell you what the circuit looks like because we're running out of time. The quantum circuit looks like the following. So x2, x1, x0. So what we have is we just apply the Hadamard on the first qubit, right? And then to get this, we actually need to apply this this control phase gate that we just discovered. So it will look something like this. So this is P1. And then I'll apply Hadamard again here. I need to do control P2. Oh, sorry, I'm missing another gate here. Why am I missing another gate is because we only looked at the second state. We only looked at this state, 0, x1, x0. There's another x2, x1, x0. And if you do the similar analysis, you'll see that I need to apply another control gate. So this will be P2. There will be Hadamard and then P1. So this is the analysis we did for the second state, right? We concluded that we need to apply Hadamard and this control phase gate. And then on the last qubit, we just needed to apply Hadamard, right? Like this. Okay. Okay, now this is different from this. So notice that this actually has the order flipped. Y0, Y1, Y2. If you look at this expression and then simplify this in this manner, you'll see that this actually ended up here, right? So Y2 actually ended up here by applying simple Hadamard. So we started from X0, but we actually ended up on Y2, which is the Hadamard. So the order is flipped. So that's also something you need to notice. We started with X2 here, ended up with Y0 here, X1, Y1, X0, Y2. So what you need to do is there's something called a swap gate. So you need to swap your state back if you want to get the correct order. So I'll need to swap this gate with this gate. Okay, if I want to swap my states back. Now, I actually, so in quantum computing, right, this swap gate is very computationally heavy to do, which what I mean by that is, so yesterday, I think Brajesh taught you that single qubit gate have this kind of noise rate, for example, Hadamard. But the control NOT gate, right? For example, I think it was the IonQ device, and it had 97% fidelity. The reason for this is 2-qubit gates are noisier than the single qubit gate. Okay, so requiring this swap gate, actually you need to do this with 3 CNOTs. So this is the circuit diagram for doing swap in terms of CNOT. You can try to verify it yourself on your free time. So doing this swap gate is a very noisy procedure. The reason why we need to swap back our state is because, remember, QFT is a subroutine. It's a subroutine within like a broader algorithm, like quantum phase estimation. So if it's a subroutine, then at the end after doing QFT, you need to make sure that your state is swapped. If this is not a subroutine and you're just doing QFT by itself, then what you can do is you can become a smarter computer scientist, right? And what you do is you actually don't do this gate at all. You'll just memorize what you started initial qubit as, and make sure this is tracked along. And then classically, once you get the measurement outcome, then you can say, okay, so measurement outcome of this corresponded to the this state, measurement outcome of this corresponded to the this state, and so on and so forth. So you don't need to do the swap if this is where the circuit ends. But if this is not where the circuit ends, then you need to swap it back. Okay, so this is another thing you need to remember. All right, so I'll move to my slides. So yeah, so this is what the circuit looks like. Now, the nice thing with this QFT is if you look at the number of operations that you applied, it will actually turn out to be log n squared. So if you count the number of gates that you did, so let me go back to my iPad again. Screen share. I think the N diagram was wrong. Yeah, Alex, can you clarify? Yeah. Do you want to unmute yourself and clarify?
Further up, where you had the circuit it shows both of the control gates coming off X0. I think the P1 should come off X1, shouldn't it? I was just thinking that when you change back to the
P1 should come off.
So on X2, you've got H, P1, P2. P1 should come off X1.
Oh, yes, absolutely. Thanks a lot. So this should indeed come off as from X1. Yeah, great observation. Thank you. That's correct. That's correct, Alex. Thanks a lot. Okay, so let's get back to the complexity analysis. I think this is the most important part of I would say this is the most important part of the QFT lecture because, or at least one of the most important parts of the QFT lecture. The reason for this is, okay, we did this procedure, we figured out a quantum way of doing it, right? Which is nice and all, but like, how many operations did we apply, right? So the question is, how many gates did I apply, right? So the answer is, I needed n plus n minus 1 plus 1. So this is n times n plus 1 divided by 2 gates. If you look at this carefully, you'll see why this is the case. Feel free to look back yourself and understand why did I need these many gates. But because we're out of time, the punchline is together, I needed order of n square because this is roughly n square, right? So order of n square gates for QFT, okay? Okay, so now this is great because what you need to understand is DFT requires, I said, 2 to the n by 2 to the n matrix, correct? FFT requires 2 to the n times n, but QFT, it requires n squared. So this is the algorithmic speed up that QFT offers. There is one caveat. You might say, okay, I applied this control phase gates, but when I actually go on hardware, how do I implement this? So you won't have to worry because there is this theorem that states, Solvay-Kitaev theorem that states that any unitary can be applied with polylogarithmic complexity on a quantum computer. So you won't have to worry that this doesn't grow exponentially when you actually implement on a quantum computer. And so this speed up still remains. And if you compare it to 2 to the n to n, right, it's an exponential improvement, right? So this is an exponential improvement.